So we are Group 6, and we're doing the Conn-Hilliard-Navier-Stokes simulations for marine free surface flows. So a little overview of our presentation. We're going to do a summary of our paper, and then we're going to show you a MATLAB simulation, our two CFD simulations, and then we're going to conclude our presentation there. So the paper, they attempted to accurately describe the free surface region using the Conn-Hilliard-Navier-Stokes models in order to optimize ship hull shapes. How did they do this? They combined the Navier-Stokes equations with the Conn-Hilliard equation for phase separation, and then they verified this combination through a 2D simulation of a submerged hydrofoil and a 3D simulation of a container vessel. In conclusion, they were able to create an alternative approach to describe the free surface region of the ocean, and then they were able to reduce computational time significantly for this method.
So for the MATLAB section, I wanted to simulate the flow around the ship and generate information about the wave profile that comes from that. Some of the key assumptions that I made is keeping it in a 2 dimensions, fixing the inlet velocity at 5 meters per second, neglecting surface tension around the water in the ship, a ship surface being non-slip, as well as saying it's only a single phase flow. We're using the Navier-Stokes governing equation for this simulation in the 2 dimensions. After running the simulation, I was able to calculate the vector profile for the velocity of each point around the ship. Knowing the velocity vector, I was also able to calculate the magnitude, and you can see that on the graph. You can see a high pressure region being formed around the sides of the ship. The highest velocity region we measured was 7.26 meters per second. You'll also see a low velocity region behind the ship at 1.8 meters per second. After knowing the velocity generated from the Navier-Stokes equation, I was able to use the Bernoulli's equation to show the pressure profile and the pressure contours. In the map, you can see different rings of different pressures. The higher pressure region I was able to simulate is 47 pascals located in the front of the boat, and the lower pressure region is actually the back of the boat at negative 14.7 pascals. It takes about one ship length after the back of the boat for the pressure to come back down to 1 pascal, which is the ambient pressure.
So starting with our CFD simulations, I was doing the laminar section. So I had to keep a Reynolds number of about 2,000, which meant my velocity was 0.002 meters per second. And some key assumptions that I had to make were that this was going to be an inviscid flow along a streamline, and it was going to be incompressible and steady state. And this allowed me to use the Bernoulli's equation in order to find the pressure profile from the velocity profile that I get from the Navier-Stokes simulation. So for the velocity, I had a max velocity of 0.0025 located at the ship's sides, and then a minimum velocity of negative 0.0004 meters per second located at the ship's stern. Now, the reason the velocity is increasing at the sides of the ship is because of the conservation of momentum and the continuity, so both Navier-Stokes and continuity equations. As the velocity splits, the mass splits, and therefore the velocity has to increase in order to keep that energy. And then it slows down when it comes back together into one mass as well. So from this, the pressure profile, we found a max pressure of 0.0022 pascals located at the ship mast when the water hits the boat, and then a minimum of negative 0.001 pascals located at the ship's sides. Now, if you notice, the pressure profiles around the ship is very low in the regions in which there is very high velocity, and that is due to the Bernoulli's equation. Now, the ship hull drag coefficient, I calculated that as well. And you can see on the graph, there was an initial contact point, very high drag coefficient, and then eventually it converged all the way down to 0.161 at approximately 1,000 seconds into the simulation.
For the turbine analysis, I'm using the actual ship dimensions to the 1/1000 scale. The first thing that we see is a concentration profile, taking downstream locations A, B, C, and D, and also a comparison of the concentration field versus the volume of fluid field from the ANSYS study. For my setup, I'm using steady state turbulent conditions at an inlet velocity of 0.012345 meters per second, SST K omega turbulence model, multi-phase, volume of fluid with a constant surface tension coefficient of 0.0625. The wave heights, which is 100% water concentration, passing the ship show at 290 millimeters is minus 3 millimeters. At 690 millimeters, it's minus 6 millimeters. At 1600 millimeters, it's minus 14 millimeters. At 2000 millimeters, it's minus 9 millimeters. These are negative values because these are all below the water line of the ship, which is the close to the free surface. The next study was the turbulent intensity along the ship hull. I'm also using a 1/1000 scale of the beam profile of the hull. For this one, I'm using steady state turbulent conditions of 0.012 meters per second with this SST K omega turbulence model, single phase. What I'm looking at is the upwind turbulence intensity increases by 7% at minus 0.1 meters. Turbulence increase also 0.7% to 11% port side and starboard at the front of the ship, and a very low turbulence along the whole of the ship, less than 5%, which is between 0.2 and 0.4 meters. Just past the ship and towards the end of the domain, I'm looking at greater than 10% turbulence intensity increase for lengths 0.4 meters and beyond. For the turbulent intensity, we can see here the velocity and pressure contours. For the computed drag coefficient, I was able to generate a 0.004 drag coefficient in the negative direction. That's negative because of the direction of the fluid flow.
So in conclusion, we were able to successfully correlate and simplify various tests performed from the paper, and then using numerical simulation and CFD simulations, we were able to extract the velocity profile, the pressure profile, the drag coefficients, and the wave heights. And that is our presentation. Thank you very much.